work out an example of a tone FM, meaning an FM modulated waveform where the input signal is a single tone. Let's just plug in some numbers for these parameters. Suppose the carrier amplitude is 10, pick your favorite unit for it. So, you know, the carrier itself will be 10 cosine 2 pi FCT, where FC is some frequency that you pick. And suppose the message signal is cosine 20 pi T. So the frequency is 10. And suppose KF is 50. KF here is 50. All right. Now, with these parameters, what is the effective bandwidth? The bandwidth that includes 99% of the power in the modulated waveform. You know, possibly 1% could be neglected. And we can say that the bandwidth is restricted in an area, in a spectrum that contains 99% of the power. Now, notice that there's something nice about FM. At the end of the day, in computing the power, you are looking at a cosine. So the power is AC squared over 2. That's pretty easy to compute. So in this case, AC is 10, AC squared over 2 is 50. So, as I said, beta is the main figure of merit for an FM waveform. Do you remember what beta is? KF KF AM over FM. Let's go back to where we defined it. KF AM over FM. Let's compute the beta for this example. KF, well, AM was specified as 1, I believe. Let's see. Yes. AM is the amplitude of the message signal, and its maximum amplitude is 1. And FM is 10, right? And KF, let's see, is 50. Oops, 50. So we get beta equals 5. So beta equals 5 is something that we're going to see a lot in the examples, because overall, as a rule of thumb, it's a good choice for designing a well-behaved, sufficiently wideband FM waveform. AM, why? AC is 10. Okay. Now, so what do we have? We have this Fourier series expansion expression, right? And we have Jn of beta, beta is 5. And now we have these spectral terms. So we have to look up somehow the values for Jn of 5. Let's go and look up values for Jn of 5. So it's good to take a look at this table a little bit, and then you will see what's going on. So when beta is small, do you remember we did this beta to the n over 2 to the n factorial approximation? When beta is small, only first few terms are appreciable. And when beta grows larger, like toward 5, for example, there are more terms that are at appreciable values. Well, this table is showing only positive values of n. Why? Because of the symmetry property of this Bessel function. Negative values are either equal to the corresponding positive values or negative of those values. So to be specific, I have it written down somewhere. Right, one moment. To be specific, Jn of beta is equal to -1 to the nj minus n of beta. So it is symmetric. So in the case of 5, if you look up the table and plug in the values, you see that to collect 0.99 or more, k equals 6 is sufficient. So what is the 0.99 coming from? Well, because we're talking about 99% of the power, and there are 2 sides, right? And the power in the cosine is 1/2. So, right. So the power in the cosine actually is immaterial here. When we collect enough terms so that total value is 0.99 or more, we have satisfied 99% of the power, right? So that for beta equals 5 turns out to be k greater or equal to 6. Okay. What does that mean? Let's list the first. No, so first we have this J0 component appearing at FC. It's this one, and corresponding negative version. And now we have 1, 2, 3, 4, 5, 6 sidebands. And of course, the other pair of sidebands. Okay. The values, the amplitudes here are controlled by the Bessel function values. Now you can see that the odd, how to mark it? The odd ones are odd symmetric and even ones are even symmetric. But the bottom line is, overall, they are spaced out by Fm. So, and we go 6 times Fm away from Fc. So this part is 60 Hertz. And there's another 60 Hertz over here. So the total span is 120 Hertz. Yes, please. From here? Here is the connection. We have an infinite number of terms here, right? But we want to say, okay, after a while, the Jn terms, as n grows, Jn terms get small. How many n terms do we need so that those terms contain 99% of the power? And we do the computation. How do we do this computation? We do this, we cannot do it in closed form because the Bessel function is very ugly. We need a computer which, you know, can compute it or look it up. theoretically, we can take a look at this table, okay, for beta equals 5, and square this, square this, square this, and add them. We go up to 6, and we gather at least 99%. You can, as exercise, you can square these values and add them and check for yourself. Okay. Okay, so let's go to that now. Does that clarify? Exactly. Why are we squaring Jn when we're doing the power? Because next to Jn we have a constant and we have a cosine, right? And when you integrate, when you square it and integrate it, the integral of the cosine is going to be 1/2. You get the idea. So the Jn squared term is going to. So basically, when you do the power computation, you will have AC squared over 2 Jn of beta squared, and from minus k to k, right? And we want this to be greater or equal to 0.99 times AC squared over 2 summation Jn squared of beta, and from minus infinity to infinity. Okay, so cancel the AC squared over 2. Okay, and this thing is 1. Oops, maybe that's the detail that's missing for you. Right. In fact, I would need to check this. Excuse me? Right. Let's check. This is the third one. This is the corresponding third one. Yes, there is some, and this is, I think the symmetry. Oh, maybe there's a typo here. There's a mistake in this picture, maybe. Let's check. Oops. So let me get another color. This is fine. 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 I think this is okay. It looks good. Huh? Okay. Yes. Omega m was given to us. See, it's here. Where's the example? It's given to us. 20 pi t. So it's 2 times 10 pi t. I mean, 10 times 2 pi t, right? Okay, so I would, so either this is 1, and we are summing this to be 0.99 or more, or somehow we know what the value of this is, and we're summing these to 0.99 of that. But you get the idea, right? So the number of significant sidebands then can be estimated by taking the number of sidebands with significant power. And we will now give you a rule of thumb that is classical in FM analysis and FM design. Here's the rule. If the modulation index is beta, it turns out only the first beta plus terms beta plus 1 terms are significant. That's pretty easy rule, right? So that's why beta is used in the design of FM very widely, because it makes the I mean, it gives you an understanding of how much bandwidth your signal is going to occupy. Because if you want to design an FM broadcast system, they're going to give you a spectrum, and you have that spectrum available to you to use, right? So that's why the first parameter that you have to live with is how widespread your modulated waveform can be. So then the power is contained in a bandwidth of 2n times FM in the case of a tone modulating signal, because we have n sidebands to the right of FC and n sidebands to the left of FC. Overall, they span 2n times FM bandwidth. Therefore, and since n is beta plus 1, this is twice beta plus 1 FM. This is known as Carson's rule. And it's coming from these beta functions. Notice that FM with a beta around 5 in our example turned out to be relatively close to 0 after n equals 6. But when beta is larger, you would have to deal with more sidebands. For example, look at beta equals 20. There is appreciable oscillation in the Bessel function up to, of course, expectedly until 20 and even more. So FM with large beta spans a large spectrum. And Carson's rule is valid in these ranges too. The spectrum goes like twice beta plus 1 times FM. In the case of a general non-sinusoidal signal, this rule of thumb also holds twice beta plus 1 times W, where W is the bandwidth of the modulating waveform. So Carson's rule actually is not a 99% rule, it's a 98% rule. Remember I said in the beginning that FM and PM mainly differ in the sense that the message bandwidth comes in the denominator in the FM expression. That means that the additive increase that causes an additive increase of the FM bandwidth with the message bandwidth. Carson rule is also valid for phase modulation, but Carson rule implies something else for PM, because for PM, beta is not KFAM over FM, right? For phase modulation, beta is KP times A. Okay, so then the effective bandwidth is twice KPA plus 1 times FM. So bandwidth expands multiplicatively with the message bandwidth. But on the other hand, for FM, frequency modulation, beta is KFAM over FM, right? So multiply out with FM, you get this expression where the expansion of the bandwidth is additive. Okay, so to finish today, note a few more things, a few more definitions. Remember, delta F is FM times beta. So we can also express the effective bandwidth as twice FM plus twice delta F. And when beta goes to 0, delta F goes to 0. So the effective bandwidth is approximately twice FM, which is consistent with conventional AM. In the wideband limit, the bandwidth expansion is controlled by delta F. Okay, so approximately it's going linearly with FM. Okay, so that's it for today.